Now I'm sharing screen. And today we continue to work with the e to linear expansion of square integrable functional from Gaussian white noise. The picture is following. We have a real separable Hilbert space H. We have Xi, which is a Gaussian white noise here. In H, which means that we have the set of scalar products with element of psi with elements of H, such that psi H is linear with respect to H, and psi H has a Gaussian distribution with zero mean and variance equal to the norm of H in square. We also suppose that our sigma field of random events is generated by Xi. Then we considered random variable alpha, which is square integrable and obtained the following representation of alpha as an orthogonal series consisting of very special objects, Qn psi xi xi, for example, where Qn is a symmetric Hilbert-Schmidt form on H, which means that for orthogonal basis EK Qn can be represented as a sum from E1 En is equal 1 to infinity. Here is Q En E I1 and the coefficients can be obtained as an action of Qn. And such norm Qn n in square is finite. equal 1 to infinity q also they are symmetric. Then we discussed that we defined Qn from xi as a sum E1 E1. Here is a symbol of weak product, which now has a very simple meaning. We just collect similar multipliers in this product and substitute degree by the Hermite polynomial of the same order. Then it occurs that Qn are orthogonal and alpha has such representation as we said. And moreover, in this representation, we have the following properties. Expectation of alpha equal Q0, that's just number. And expectation of alpha square is equal to the sum from n equals 0 to infinity, norm Qn n square multiplied by the n factorial. We discussed that this representation is unique. And question is how to get it. One of the possible ways is the calculations of the product with the stochastic exponent. We defined last time stochastic exponent for element H which belong to our Hilbert space as follows. E of H is equal to exponent of the xi of the scalar product of our white noise xi with H minus 1/2 of norm of H square. It is trivial to see that this random variable has any moments, not only a second. So one can consider the Fourier-Wiener transform of alpha of our random variables, which depend on H as an argument and is defined as an expectation of alpha multiply on H. This In order to understand why this Fourier transform is so nice and useful when working with e-to-Wiener expansion of Gaussian functionals, it is necessary to understand what is the e-to-Wiener expansion of stochastic exponent itself. Last lecture we finished it with the following. Let us denote by the H with tilde, normalized vector H. Then the stochastic exponent of the element H can be expressed as follows. This is exponent. Here we will have norm of H. Here xi H tilde minus norm of H square divided by 2 And using the well-known for us already form of the exponential generated function for Hermite polynomials, one can see that it is equal to sum from n equals 0 to infinity. Here is norm of h n factorial divided by n power divided by n factorial, and here is Hermite polynomial of degree n from psi h tilde. I'm claiming that this is exactly e to Wiener expansion of our random variables. Moreover, that this hn psi h tilde is the value of such special symmetric Hilbert-Schmidt form from psi psi psi. To see this, one can mention the following. The first one, let us say that this is a proof. The first one, let us note that for any m and which is not equal to n, which is not equal to n, we have that for any qm belonging to h tensor m symmetric, expectation of qm psi 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 multiply on the h n psi h tilde is equal to 0. So from here we understand, please check this using the properties of Hermite polynomials, that they are orthogonal polynomials with respect to Gaussian measure. This is one. And second property which we need for this can be obtained as follows. Let us take again orthonormal basis, EK is, as usual, normal basis. Then one can express our stochastic exponent from H in terms of EK. So it will be exponent. Here is norm of H multiply on the sum from k equal 1 to infinity. Here is psi ek multiply on ek h tilde minus 1/2 sum from k equal 1 to infinity. Here is ek h square multiply on the norm of h square. Yeah, I just use Parseval identity and the fact that h with tilde has norm equal to 1. Now it can be written as a product from k equal 1 to infinity. Here is exponent norm of h ek h with tilde. Here is psi ek minus norm of h square ek h square over 2. And then now using again exponential generating function for Hermite polynomials, one can get that it is equal to the product from k equal 1 to infinity. Here is sum from ek equal 1 to infinity, norm of h in ek power ek h with tilde in ek power divided by ek factorial and Hermite polynomial h ek psi e ek. Yeah. Okay. What is remaining? It is remaining to rewrite this as we usually have the Fourier e-to-winner expansion. So I will collect the terms with the same norm of h in the same power. So from n equals 0 to infinity, norm of h in n power. And here I will have exactly the sum from ek e1 ek en equal to 1 to infinity. Excuse me. En equal 1 to infinity. Here is e1 h tilde en h tilde multiply on the you see here for Hermite polynomials. So here I put psi, excuse me, psi e1 with product psi en, and it is exactly equal to the sum from n equals 0 to infinity. Here is norm of h n. Here is h tilde n time from psi. By the way, in these calculations, there, please pay attention why disappears this ek factorial in denominator. It disappears because of permutations there. Yeah, because of permutation in the sum. We can have, for example, the same index we can have on different places. And from changing of these places, nothing change. So this ek factorial will cancel it. Yeah. This is the idea. Please check this carefully. So we have such equality, and I can continue, because when we multiply tensor product on some number in power n, then I can put one multiplier here, one multiplier here, one multiplier here, and so on. In this way, I can get a much more beautiful formula. So it is equal the sum from n equal 0 to infinity. Here is h without tilde. H and time from psi, psi, psi. This is a final form of representation for stochastic exponent, and using it, it is trivial to see that now we have the very nice representation for Fourier-Wiener transform. It can be expressed as follows. This expectation of alpha multiply on EH. So it is expectation of the product of two Ito-Wiener series. One is the general for our random variable alpha, and it has a form Qn psi psi psi. And another one is the series for our stochastic exponent we just obtained. So here we have the sum from n equals 0 to infinity. Here is h n psi psi psi. So using the properties of the Ito-Wiener expansion, one can get that it is a series sum from n equals 0 to infinity 1 over n factorial. Oh, excuse me, n factorial. N factorial here is Qn from h. Now the substitution is as usual. We have deterministic vector h substituted into multilinear form Qn. Finally, we get the following formula. And from here, one can check that Fourier-Wiener transform is an analytic function on H. So it is a sum of power series on our space H. And how one can recover now Qn? Qn are just coefficient of Fourier-Wiener transform. So one can say that now our Qn can be recovered as follows. Qn is just let us denote it, n's derivative of tau alpha h over n factorial square, yeah, and everything must be calculated at point h equal to 0. So from this formula, one can see that using Fourier transform, we can recover the coefficients of e to Wiener expansion for arbitrary random variable. We will use this in the future. But now, since we already know that Fourier transform is in one-to-one correspondence with the square integrable Gaussian functions, one can try to define weak product in more general situation. So let me produce the definition. So general definition of weak product definition. The weak product of alpha and beta belonging to L2 omega, excuse me, omega Fp is well defined if there exists gamma belonging to L2 omega Fp such that for all h belonging to h, tau alpha h multiply on tau beta h is equal tau gamma h. In this case, weak product is equal to nil. That's all. So we have the following definition, and maybe you remember one-dimensional case where we did the same. Now we did this in the general case, and from this definition, it easily can be seen that weak product, if it is well defined, has interesting property. First of all, it is commutative. In case, of course, it is well defined because here we can interchange multipliers for free. So weak product is commutative. Slightly difficult is to check that it has associative property. For us, some its properties are interesting related to Gaussian structure of our space. So let's consider some properties of weak product. When as a multipliers, we will use some Gaussian or Gaussian variables like xi multiply on something or Hermite polynomials from these variables. So it can be seen that now I want to check properties of the weak product for some special random variables, namely for the elements of Ito-Wiener expansion. Yeah? So let's check properties. First of all, let us recall that if we have some Qn from xi from H, then it is equal Q and H. So it is well defined and very simply calculated. From this, I can check that for any Hn belonging to H, then the n power symmetric part, Bm belonging to H m power symmetric part, one can have the following. An from xi weak product with Bm from xi is well defined. In order to check this, what I have to do? I have to present the result of this weak product. Okay, let me do this. And I will do this as follows. Let us define, indeed, define Cn plus m form as the following. It is, let me explain after. This is lambda an multiply on bm. Here, lambda is a symmetrization. What does this mean? For all phi n plus m belonging to H, let us consider A n phi 1 phi n multiplied by Bm phi n plus 1 phi n plus m. Then such map from H n plus 1 to R is, of course, n plus m linear Hilbert-Schmidt form. Please check linearity is trivial, that it is Hilbert-Schmidt follows from the fact that an and bm itself are Hilbert-Schmidt forms. So form. So we have n plus m linear Hilbert-Schmidt form, but it is not symmetric. And finally, lambda an multiply on bm is a symmetrization. So now I have such Cn plus m, and I am claiming that now the following holds. Cn plus m from xi is exactly the weak product An xi Bm Bm xi. To check this, now it is trivial. Tau of Cn plus m xi from H, as we know now, is equal to Cn plus m from H. It is equal to lambda An from excuse me, multiply on Bm from H. But now I am substituting into the Hilbert-Schmidt form the same elements, the same. So I can just omit this symmetrization. Yeah. So I can continue writing. It is equal to An HHH, and here is Bm HHH, and this is just tau An xi from H, and here is tau Bn Bm xi from H. Okay, that's all. This is the end of the proof. And let me emphasize that somewhere here we have a mistake. Oh, here is it. I forgot about I forgot here 1 over n factorial. Yeah, 1 over n factorial in the expression for stochastic exponent, and here is 1 over n factorial. 1 over n factorial. Please check this. Then we have here, we have no here any factorial. And here we have no this denominator. Okay. This is just 1. Okay. Okay. Please, please check this. Yeah. Mhm. Okay. So now we see that our weak product for two multilinear forms from Xi is well defined. And by the way, it can be seen that it is not coincide with usual product. Yes. We already have seen the same in one-dimensional case when it occurs that weak product of two Hermite polynomials from the same standard Gaussian random variable is equal to the Hermite polynomial again. Yeah, the same happens there. Weak product of two multilinear Hilbert-Schmidt forms from Xi occurs to be again multilinear form from Xi. So it is interesting to see when the weak product coincides with the usual product. And it occurs that such cases exist. Namely, suppose that assume that L1 let's not let's use another letter, M1 and M2 are orthogonal subspaces of H, which means that for every X belonging to M1, Y belonging to M2, we have that the scalar product is equal to 0. Now suppose that AN and BM, those multilinear Hilbert-Schmidt forms, are such that AN from phi1, Yn equal to 0 if at least one Fi is orthogonal to M1. So it means that An from phi n Tn is equal to An from P1, 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 Pn, where P1 is a projection of excuse me onto M1. Of course, when I say projection, I mean orthogonal projection as every time when we work in Hilbert space. Now, the same, suppose it's the same about BM and M2. Then them B, okay, not B, excuse me, AN psi weak product BM psi is exactly the same as simply a product AN psi BM psi. So in this case, we have the equality that the product of our multilinear symmetric Hilbert-Schmidt form cross I in the usual sense is exactly the same as in the weak sense. Yeah. Let's let's have a proof, and after this we will discuss what does it mean. Proof. So what we have to do? Of course, we have to define this Cn plus m, which is lambda of the product, An multiply on Bm. Yeah. Okay. Then let us work with this. Let us work with this symmetrization and see what will happen. See what will happen. In order to do this, I will represent. Okay, I will let us take any H which belongs to our space H. Then, oh, maybe not even H, but let me define symmetrization. So I will take already phi n plus m, which belongs to our space H. Then what I want to do to define symmetrization, first of all, let's consider An from phi1 phi n multiply Bm. Here is phi n plus 1 phi m. Then what I can do? I can continue using this equality. That actually, when we consider our Hilbert-Schmidt forms, due to the condition, we have that this Hilbert-Schmidt form are mostly concentrated on M1 and M2. Yeah. So let us go back, and we will see that this is exactly the same as IN. Here is P1, phi1, P1, phi n. And here we must do the same. Bm, P2, phi n plus 1, and P2, phi m. Okay. Now I want to have symmetrization. I want to have symmetrization and to discuss what happened when we will define the action of this symmetrization on the basis elements. So I will continue with the following. Let us take orthonormal basis in H of the following structure. I will get EK prime. I will say that is orthonormal basis in M1. Then EK2 prime is orthonormal basis in M2, and we have to put some additional vectors because we don't know about linear span of M1 and M2. It can be not all, it can be not generating all H. So EK3 prime is orthonormal basis in H minus here is M1 plus M2. Okay. So then when defining lambda an bm psi, what I have to consider, I will get the sum. I will get initially, let me say, the sum from all bases. I say EI prime, EJ 2 prime, EK 3 prime. Yes? With all these indices from 1 to infinity, and number of indices will be equal n plus m. But see what happened. Here I will have the following coefficients. Lambda an from these vectors, bm from these vectors. Yes? But let me say to you that due to such properties, here we will have non-zero only when all elements belong to the first basis, ek prime. Here we will have non-zero only when all elements are from the second basis. Yes, that's all. So I will have the following. Let's continue writing. Yeah, it will be the sum. It will be the sum from E1, En equal 1 to infinity, maybe long sum. J1, Jm equal 1 to infinity. And here is An, E1 prime, En prime, Bm, J1 2 prime, Jm 2 prime. Multiply on the weak product. Here is psi E1 prime, psi En prime, multiply what I have to write. Let us put here the question, and here is psi J1 prime, and so on. Psi Jm prime. Yeah. But you remember how we produce weak product of the such random variables obtained as a product of our psi on the elements of basis. We just collect similar one, but there are no similar one here and here. There are no. So instead of the weak product, we can put here just multiplication. Because again, there are no any similar multipliers here and here. Due to this fact, now one can continue with the formula An from psi and Bm psi. So in this case, weak product coincide with the usual product. That's the end of the proof. And it is a very interesting thing. Let me explain why. Remark. Let us consider restriction of xi on M1 and restriction of Xi on M2. They are independent. Really, they are jointly Gaussian, and they have zero correlation due to this normal correlation. Zero. So initially, AN from Xi, and BM from Xi are independent. And one can begin to think that this is general property. If we have two independent random variables, then always the weak product is well defined and equal to the usual product. It is not true. They must to be independent in the some very special sense. You see, they are generated by the restriction of Xi onto orthogonal subspaces. So the independency much more stronger than usual independence, than usual definition. But if this much more strong property holds, then weak products coincide with the usual product. So please pay attention to this remark. Okay, so today we discussed the stochastic exponent, recovering Ito-Wiener expansion using stochastic exponent. We defined a weak product and see that it is well defined in many cases, and for independent in special sense, Gaussian functionals weak product coincide with the usual product. Maybe it is time to go to the application. So tomorrow we begin to apply all this knowledge to some special example when Xi is defined as a formal derivative of the Wiener process. For today, this is all. Thank you for attention. Maybe somebody have questions or comments, please. Okay, if there are no questions, then thank you for attention and see you tomorrow.